Good morning, friends. It's Ben, and this is a video for the Vector Calc class. We are looking at separable differential equations. This is my second attempt at the video. I discovered that if you reboot an iPad, it actually erases information that you had on the screen. Shouldn't be a surprise, but it was. So in any case, bear with me a little bit here as I might forget some of what I haven't said yet, if you see what I mean, because I think I've said it already. All right, so with these separable differential equations, I'm stalling a little bit here because I have to erase some of my side work here. With these separable differential equations, the notion that you have is that you have a dy dt or dy dx, whatever variables it could be. We saw an example on the previous assignment where it was dx dt, right? But you have your independent and your dependent variable, and you've got dy dt solved for. If it's separable, it will turn out that you can factor it completely into a function of t alone and a function of y alone. That's what it means to be separable. And if you can do that, we treat it as though the dy and the dt separated into two pieces. It's not really what's happening. It's just a formal manipulation, but it's a formal manipulation that is logically consistent. So we use it a lot to save time and ink, well, pixels. So let's take a look here at what we do in that case. And here is hoping that the iPad decides to connect. Here we go. Yay, it did. All right. So as you can see here, separable DEs are going to be the ones that will separate, right, into this piece and this piece. So when you do that, then you can algebra this thing and put the y's on one side and the t's on the other, and do an integral, an indefinite integral with respect to each one. Now, when you do that, there's multiple levels of deception there. Number one thing is that when you say dy dt, you really are not integrating with respect to y. Y is a function of t, but this dy represents dy dt times dt. So it's like a u substitution. It's just a u substitution where you don't actually know what the u function was. That's seems a little bit awkward, right? But that's what's going on. It is a formal manipulation there. The other thing is that when you do indefinite integrals, technically speaking, there is not such a thing as an indefinite integral. People who are being super formal about these things would go ahead and do their definite integrals on both sides and have the limit of integration for this side be from the y naught given an initial condition up to the y value that you're talking about, and then you'd have to introduce a whole new variable there. And then on this side, the limits would be from t up to whatever the t naught is, or actually reverse that. The y naught and t naught are the lower limits, I guess. But we tend not to do that. We tend to just put a plus c. And there's a caution that I'll show you with this super short example here in a second. Don't write two different c's. Okay, that's the other kind of level of deception. There will be a plus c from this and a plus c from that. They will not be the same plus c. They do not cancel out. Now, if you're clever and say, all right, I'll make this one have a plus c1 and this one be a plus c2, fine, have a field day. You're writing extra stuff, but maybe you just enjoy to write. So when you do that, then you end up subtracting the c2 over to this side, and your c1 minus c2 becomes a new single c. So, all right. So if we look at what we're doing here, we say dy dt equals y. You might say, oh no, there's no t. Well, think of the function of t being just the constant 1, okay? And then we break it apart and put the dt on the right side and the y on the left side, so that it's all y's on the left and all t's on the right. If you have something with some t's on the left and some t's on the right, and or some y's on each side, the same difference, you can't integrate it. It has to be all one variable, okay? So once you've got that, then you integrate. I will just write an integral symbol, okay? And dy over y, of course, is log y, and integral of dt is just t. We put the plus c on the right-hand side. That's just a convention. The right-hand side is just where we put it. So now we've got an answer. And if you're happy with that answer, great, leave it that way. But most of the time, people want to solve for their y. How do you get a y out of a logarithm? With an exponential. So you exponentiate that, and on the left side, it cancels. On the right side, you have e to the t plus c. Now, e to the t plus c is really the same as e to the t times e to the c. And this e to the c is a constant. It's not the same constant as the c was. So we label it y sub naught because it happens to be the value that y is going to take on when t is equal to 0. But oftentimes I will just write c in this spot, or k, or just whatever letter comes to my mind at that point in time. So a lot of times you're doing these manipulations, and your formal manipulation is that you let the constant absorb things. It's okay to do that as long as what you do is okay to do. I didn't explain that very well, and I realize that. It's something that you kind of figure out as you go along, all right? Okay, so let's go ahead and solve a differential equation here. And you will notice down in the lower right-hand corner, I made myself a note. We're going to look at this on a graph using Desmos. That is part of the reason why this is my second attempt. And so, all right, so I'm going to go ahead and just copy that equation down. dy dx equals x squared over 1 minus y squared, right? So if you see that and immediately think, oh, I need to factor 1 minus y squared into 1 plus y and 1 minus y, and I have to do partial fractions, don't. The thing that we'll do here is to see that we have 1 minus y squared times dy, and that's going to be equal to x squared times dx. We pretended that dy and dx were separate quantities, and we multiplied both sides by the dx, and we multiplied both sides by the 1 minus y squared. And now we have things set up where it's only x's and only y's on the respective sides. So this isn't too hard to actually do the integration for. And we'll end up with that there, right? And I'm going to tidy it up a little bit. I don't like having fractions. If you see a bunch of fractions floating around and you're going to leave it as an implicit solution anyway, you might as well get rid of the fractions. So I will have y, or 3y minus y cubed equals x cubed. And instead of 3c, I'm just going to write c, because the c will absorb the 3, right? And then my solution that I'm going to leave it as is this. Now, you might say, Ben, why don't you solve for y? And at that point, I'll say, because of this guy right here. Y cubed means we could solve this, but we have to go refer to the cubic formula. Go Google that, see what it looks like, and you'll see why I'm going to leave it as an implicit solution. All right, so let's jump over to Desmos and see a plot of this. And what I've done here is to put the C on the right-hand side, and I made a slider. The reason I made a slider is so that we could look at what happens as we change it. for those different values of C, we get things that it all looks kind of the same, but right in this regime here, see how it did that weird thing? And it's kind of symmetric on both sides of the possible C values. When you have a fold like that in a graph, it indicates that there's a problem, right? This is a practical sort of thing. If you look at something and you've got this kind of S-shaped fold and you're doing something with potential energies or something like that, there is a tendency to have solutions that are moving alongst this graph, and when they get to one of those cusps like that, they fall from one solution to another, from one branch of the solution to another. And that is super simplified and ignoring bunches of stuff, but it's related to a field of math called catastrophe theory. And it's about what you think it's about. It was very popular for a while, like decades ago, and then the whole field kind of dispersed at about the same time as chaos theory became big. So, all right. So that's what our solutions look like there. And you can see what's happening as we have different values of C chosen. All right, let's hop back and look at another of these. So this one's asking us to find just a different one, but when we take a look, we can see the numerator is all X's and the denominator is all Y's. So it's going to work very similarly. So I'm going to just copy the stuff that I need there and have the 2 times y minus 1 dy is equal to the 3x squared minus 4x plus 2 plus 2 dx, and then I'm going to integrate it, right? So you can see that you would have the 2y, so that's going to get me a y squared, and then the minus 2 will get me a minus 2y, and then this is equal to x cubed minus 2x squared plus 2x, and then plus c, okay? So, and I should not have put an equals in between those. So that's getting us an implicit solution. And we're going to jump across there and take a look at a graph of that. But before we do, let me make the point. This time we actually can solve for the y. If you are a masochist, you will solve for the y by doing some version of the quadratic formula. But a simple thing to do here is to come along and say y squared minus 2y plus 1 is equal to my x cubed minus 2x squared plus 2x plus c, and I changed fonts for my c because I added a 1 to it, okay? It's just a slightly different c value. And that means that this left-hand side is really y minus 1 squared. So now we can say y minus 1 is the square root of x cubed minus 2x squared plus 2x plus c. So when I did that, I hope all of you shouted at the screen, because that's a little bit of a mistake. Really, I should have written it's plus or minus the square root, right? And then for a solution, you can say y equals 1 plus or minus the square root of all this business. And if you look back here and see that we've got y of 0 equals -1, then we're going to have to plug in to one of these things. And if you plug in your -1 for the y, and 1 plus or minus a square root, all the other stuff is 0, but you've got a c here. C here, right? Now, if you choose plus, it is not possible to find a value of C that will make this work. If you choose this to be minus, then there is a solution. So we're going to do the minus. And hopefully y'all will catch that. And so we have -2 is equal to minus the square root of C. See what I mean? About then it's possible. And so you'll solve and figure out that your C is going to be 4. And so then we will come back and just put the 4 in here. Okay. All right. So keep that all in mind, and we're going to jump over to Desmos again, and I will turn off that graph and turn on the next one. So this is the implicit solution we have, that for different C values that you'll get something like this. It looks a little bit like the Witch of Agnesi, or Agnesi. I don't speak Italian, so I'm probably getting the pronunciation wrong. But if you want it to go through the point 0, -1, that was given as an initial condition, then you have to choose your C value just right, okay? So if you notice there, the C I've got is equal to 3, but remember that's the C before you added 1 to both sides, okay? And when you want to do an explicit solution here, then you end up getting that portion there. Now, zooming in a bit here, I want y'all to notice what's happened here. It's gone up and folded over, and you don't get any solutions that go any farther up, and you don't get any solution that goes any farther to the left. And you might be kind of curious about that, because we talked a little bit about existence and uniqueness, and you always get a solution so long as that f of ty is, unique, not unique, continuous. And I'm sorry, the f of ty and its derivative with respect to y. But if you look back there to what it had, you'll notice that this point here has a y value of 1. And in the f of ty, you had, what was it, 1 minus y squared appearing. That 1 minus y squared in the denominator, when you get y equal to, 0, that meant the f of ty was undefined, okay? Then another interesting bit, look at this stuff that's under the square root here, okay? I can't highlight it because it's on a different screen, okay. Look at the stuff that's under the square root, and if I were to graph that, it turns out to hit the y-axis here at this -0.881, right? And if we went up here, can't get it. Yeah, I can't get it to quite zoom in. It looks like it's it's trying to do the red one, and I want it to do the black one. Okay, try to remember that number, -0.881, and let's see if that's come on, dude. It won't get any closer. Sorry, but it's getting close there to the -0.881. So exactly the place where the square root stuff turns into 0, and I can't make it do it again, where the square root stuff turns into 0, and that's where square roots are no longer defined when they become negative. So we've got a strong association going on with that sort of thing. All right, so let's jump back and look at another problem here. And so for this setup, we've got the dy dx equals y times cosine x, and then divided by 1 plus 2y squared. If I go ahead and and move things around, I started to put the 2y squared in the wrong place there. Let me try that again. I will have the 1 plus 2y squared over y, because we had to flip it over. dy is equal to the cosine x dx. Okay. So then that's simply 1 over y plus 2y dy equals cosine x dx. And I can integrate that fairly easily and have log y, and I said equals again. I shouldn't have. Log y plus y squared. I'm not going to put my plus c over here. I'm going to shove it over here. And then sine x plus my c. Okay. Now, that is an implicit solution, and we're stuck with it. The thing we've got here is a transcendental function and a logarithmic function put together. There are solutions for this, but they're solutions that are not going to be in terms of the functions that we're used to. So we're just kind of stuck with this for now. And let's take a look. Oh, actually, I was going to look back here at, yeah, something. If we're talking about continuity stuff, it looks like we don't have any problems with the function of the y and the function of the x, but when you move over to the other side, y equals 0 looks like it's causing some sort of problems in there and stuff. Now, all right. So here on Desmos, we'll turn that off and we'll turn this one on. Now, there is one slightly awkward thing about the notation here. If you notice, I had to type in not lny, but log y. Mathematicians outside of regular sciences and stuff, we never refer to ln. We always refer to log because we only use the natural log. The other bases of logs are kind of a fiction. That's it's not really a fiction. It's where logs originated from, but yeah, they can all be done in terms of a natural log. So we always use just log to mean natural log. All right. So then our solution there is probably not too much of a surprise that it has some sort of a wave in it. But as we change the c, watch what happens here. Let's see if we push the c up higher. Notice how it gets higher, but it also flattens out as it goes. If we push the c down lower, we get closer and closer to the axis there. And did you notice that? It just starts flattening out, and it doesn't want to get below the axis. That's because you've got a log of y in your solution. So you can't actually have negative numbers allowed for y. And as we flatten out there, it's not entirely easy to see that this is happening. Let me try to crush in the x direction and out the y direction. Okay, you see that those little bumps there? And as I continue to make my c smaller and smaller, they get smaller and smaller, and eventually there's like these little blue areas on the line, and there's nothing defined in between. You get gaps in the domain. So yeah, these implicit solutions sometimes are not going to give you something that is entirely, continuous. But all right. Anyway, let's hop back over here. Now, when I was getting ready to do this problem, I actually originally did it the wrong way and mixed up my x's and my y's. And I found that there's kind of an interesting thing that happens when you do that. So I set up an initial value problem here that was just swapping those x's and those y's to see what would go on. And I had to kind of play with it a little bit to get the initial condition to be something that made sense, right? And you'll see why as we go along. So if we do this, you'll get a dy divided by cosine y. So that means essentially you got a secant y over there is equal to an x dx divided by 1 plus 2x squared. And so you got these things that you'll integrate there. So on the left part of it, you're integrating secant. And so if you look that up, it's a log absolute secant y plus tangent y. And we should say a plus c, but we're going to transfer it to the other side. And then the other side, you're going to have a u sub that you'll do. The u is going to be the 1 plus 2x squared. And so that means that you end up with a 1/4 here, logarithm absolute value of 1 plus 2y squared. And then we'll put the plus c here. Since you have logs on both sides, it's super duper obvious that we ought to be taking exponentials. But keep in mind that when you take exponentials and you get that 1/4, that will turn into a power. So we will have secant y plus tangent y is equal to quantity 1 plus 2y squared to the 1/4. And then because that would be an e to the c being multiplied by it, I'll put my c there, okay? Pretty messy. But now you really are in a situation that you can't do too much. You really have to know some tricks to get that y out there. So, oh, and as I went along there, y'all are probably yelling at the screen because of the dumb thing that I wrote. Man, all right, that was supposed to be an X in there. All right. Okay, but yeah, we can't, we could probably get that y out, but when we do, we're going to lose a little bit of what's going on. So jumping across to Desmos again, I am going to turn off the previous one. Oh, I'd forgotten with the previous one that I was wanting to get C values that would go through that point. Aha. So anyway, let's turn that off. And so we're going to look at this secant. Now you're looking, or the secant and tangent thing. Now you're looking at it and you're thinking, okay, that doesn't look too bad. It's, you know, it looks kind of like an upside down normal curve maybe and stuff. But part of why you think that is that the range has been restricted. Secant and tangent are periodic, and that means that we have solutions going up and down the y-axis there. So as we change our C value, there was something that was kind of weird about Desmos with this. I don't know if you'll notice it, but it's kind of laggy as I do this. Did you? Oh yeah, you saw it. I'm sure you saw the jumps there. That just at some values, it just takes a little while to calculate. So if we had an initial condition, what did I say it was? Y of 0 equals pi over 4. So that means that we need to look for that point. Maybe I'll go ahead and just put parentheses 0, comma, pi over 4. And I'll put a label on it and everything. All right, so now we can see where it's at. And take our C values and okay, here's where the jumping around is going to be a problem. Yeah, I can get one of those to come through there, and it looks like it's around C equals 2.4. we could sit there and plug in the pi over 4 on the left-hand side and the 0 on the right-hand side and figure out what the C is. But yeah, that's the kind of thing that's happening. All right, so I think that was all. Yeah, that was the last of the examples there. So separable differential equations, the main hassle is if the integration turns out to be nasty. If it turns out to be nasty, consult an internet resource and get some help on the integration. Don't go there immediately. If you have to go to an internet resource to do power rule or integration by parts stuff, I'm going to kind of look at you funny. But if you have to go in order to do a trig substitution or a hyperbolic trig substitution or some of the crazy stuff like that, okay, yeah, I get it. All right. So if the integration's easy, do it by hand. If it's not easy, go to something else to help you out with that. But try it first. Okay. As a matter of fact, even if after you got it, check yourself. All right. If you think you spot an error on my answer key, maybe check to make sure your integration's right before telling me that I'm wrong. Because you'll hurt my feelings, All right. Anyway, I will see you all in class. This probably is not going to be that rough of an assignment, but yeah, we'll see how it goes. All right.